Today's topic is overall heat transfer coefficient. So when we are dealing with the problem of a fluid to fluid heat transfer across a metal body, means what? If a condition is there, here it is the hot body and this one is the cold body. Now definitely heat will flow from hot body to the cold body. And now suppose a pipe carrying hot fluid, it will transfer heat to the surrounding, right, through this metal wall. So in this type of example, there is a concept of overall heat transfer coefficient, in which the overall heat transfer coefficient, which is denoted by capital U, which gives the heat transmitted per unit area, per unit time, per degree temperature difference between the bulk fluids on each side of metal. Means for the both side you can define U. So as we know that here it is the convection, through this metal wall there is a conduction, and through again this cold fluid there is a convection. So let's find out the equations. If I want to find out heat flow rate Q, which is equal to HHF, means what? This is the coefficient of heat transfer coefficient, right? H, heat transfer coefficient. A is the area, this area, surface area. THF is this temperature and T1 is the temperature of this point. Now at this location only heat will transfer, or we can calculate the heat transfer with this formula. Similarly, you can use this formula where HCF is the cold fluid heat transfer coefficient. For this cold fluid you can calculate heat transfer. And tell me, what is the formula for Q which we are going to use for metal wall? For this one, by taking these two temperatures T1 and T2, right, it is equal to Ka into bracket T1 minus T2 divided by L. L means the thickness of this wall, right? A means the area, this one area, cross sectional area, since we have to take the perpendicular area to the Q, this area, vertical. And K is the thermal conductivity of this metal wall. Now by using these inputs we can find the separately Q at each and every junction, means at this place, at this place and at this one. Now if I take these three equations, remember how we have find out this? These are the standard equations we have taken together, right? Now in this equation, if I rewrite these equations in this way, simply putting the temperature difference on the left side and whatever the remaining terms, it will come to the right side. I can write for conduction also. So T1 minus T2 Q into L upon Ka. Similarly, I can write for convection, for the cold convection, right? Now we are having these three equations. If you look into these three equations, now tell me, if I add these three equations, I will get on the left side THF minus TCF, right? So let's do it. So THF minus TCF, these are the temperatures at the hot fluid and cold fluid temperatures, is equal to Q, which is common, I have taken from these three. Inside the bracket 1 upon H, this is the heat transfer coefficient for hot fluid, into area plus L upon Ka, L is the thickness of that slab, K is the thermal conductivity, plus 1 upon HCF, H is the heat transfer coefficient and A is the area. Let's take A outside of this bracket, since for all these three modes the area is constant. So if I take to the left hand side, I will get this equation, right? So rewrite this equation for Q. So Q, which is equal to this one. So if I convert this equation in a standard form, should I write Q is equal to UA inside the bracket the temperature difference? Now can you tell me what is the U? Yes, it is overall heat transfer coefficient, and it should be, if I equate these two equations, then you will get the value of U, which is equal to 1 upon, inside the bracket, 1 upon H plus L upon K plus 1 upon HC. So how to remember this equation? Simply U is equal to 1 upon the thermal resistances, right? And inside this thermal resistances, what you have to do, you need to take the reciprocal, means simply remove the A term, right? Yes, it is. You need to remove the A terms. So L upon Ka, 1 upon Hf, 1 upon HCF are the thermal resistances. So let's take one example. A mild steel tank of wall thickness 12 millimeter. Remember, you need to read it carefully. Sometimes it is in centimeter, sometimes it is in meter. So you need to convert this into meter. Let it be. Contains water at 95 degrees Celsius. Thermal conductivity of mild steel is 50 watt per meter degree Celsius, and heat transfer coefficient for the inside and outside the tank. Now see here, inside the tank there is a water at 95 degrees Celsius. So here it is 2850 watt per meter square degree Celsius, and heat transfer coefficient 10 for the outside. If the atmospheric temperature is at 15 degrees Celsius, calculate rate of heat loss per meter square, the temperature of outside surface of the tank. Let's convert this example graphically. So I have taken only the part of this tank. So you may consider here, this one is the tank, right? So instead of total tank, I have taken one cross section of that tank. So inside of that tank there is a water which is at 95 degrees Celsius, and outside there is a air. So heat will flow from inside to the outside, since I have taken water which is higher temperature than the air. Air is at 15 degrees Celsius. Now thickness of wall, which is equal to 12 millimeter, simply convert it into meter, and this will be the length, right? Temperature of water 95 degrees Celsius, we called it as THF. Temperature of atmospheric air 15 degrees Celsius, we can call it as TCF. Thermal conductivity of mild steel K, which is equal to 50 watt per meter degree Celsius, and heat transfer coefficient inside and outside. So let's find out this inside. For inside there is a hot fluid, so I will denote it as HHF, and for cold means air, it is at less temperature than this hot water, so I will call it as HCF. So by taking these inputs, what I have to find out? Rate of heat loss per meter square. And since we know this situation is particularly where the overall heat transfer coefficient situation, So should I write here Q is equal to UA into the temperature differences, fluid temperature differences? Is it? Now what does it mean by U? It is overall heat transfer coefficient. So let's find out this U, which is equal to, now instead of taking U is equal to 1 upon this term, I have taken 1 upon U is equal to this one. So let's find out. We know the value of HHF, L, K and HCF. By this means you will get the value of 1 upon U, which is equal to 0.1006. Now we need to find out U, right? So U is equal to 1 upon 0.1006. So it will be equal to 9.94 watt per meter square degree Celsius. By means of definition only, overall heat transfer coefficient definition, we got this unit, right? So now I have to use this formula, right? So Q is equal to U into bracket this one. Simply while rewriting this equation, one change is there, Q upon A. A is at right side, take to the left hand side. So 9.94 inside the bracket, the temperature difference, you will get this 795.2. Now tell me the unit. Yes, watt per meter square. Rate of heat loss per meter square. So watt per meter square. So this will be the Q upon A. Now the temperature of the outside surface of tank means the temperature T2. Since we know the value of this one Q upon A by using this formula, so if I write Q is equal to HCF A inside the bracket T2 minus T1, sorry, T2 minus TCF, here it is TCF, right? Because I need to find out the heat transfer through the convection. So T2 minus 15 I have to take here. So I can rewrite this equation for Q upon A, since we know the value of Q upon A. Now here we know the value of HCF, Q upon A, and T1. T1 means this one, TCF, right? Here TCF is 15. So by this means I will get the value of T2, the temperature of outside surface of the tank. Thank you very much.